Let's do this. Review for the final. A few of the details of things we've learned through our little time here.
This is what I'm feeling for the final. I think the final should look exactly like this and review sheet.
The final won't necessarily look just like this, but similar, I guess. All right. So we found really a lot of the class was integrals, but we did start with a few things about derivatives, like find the derivative of, well, logarithms. We found derivatives of logarithms and exponentials. I don't have up here the sine inverse, but remember those derivatives are on the rule sheet that I provide there. So, of course, here, for example, we're using, on number 1, chain rule 2, right? So anyway, what's the derivative of logarithm? Well, again, that's on the sheet. Yeah, you had it memorized. Well, if it's natural log, it's just 1 over what's inside the ln, right? But if it's logarithm another base, here's what we do. It is still 1 over the inside part, which is e x minus 4x. But we have to multiply on the bottom by, remember, the natural log of the two, the base. So you have to multiply by the ln of the base. And then one other part to that is times the inside derivative. Derivative of the inside would be e to the x minus 4. Oops. This all looks new to you, is that what you're saying? Okay, it's been a while for other base other than log, ln's. But now what about, so the second part, oh, that was a minus. Why did I erase that? Second part is minus, all right, so this exponential, remember if you have an exponential, maybe I should write that the derivative of a base, the base of a, you know, if it was e to the x, it'd just be e to the x, right, derivative. But a to the x is a to the x times ln of a, yeah. Now this has the other part to it, chain rule. So I've got 5 to the ln of x squared plus 4 times the ln of 5. But what's the other part? Derivative of the inside? Well, the derivative of the inside, the power, well, I've got ln, so that would be, the derivative of it would be 1 over x squared plus 4. What else? Derivative of the inside, which is 2x. Okay. I guess we could clean it up. We could combine things. Think that looks good? What? No, it's not quite going to cancel because that it's e to the x minus 4. This one is e to the x minus 4x. So it almost canceled. I don't know how we clean that up. I don't know how I'd want to write that, but it's not going to clean up very well at all, so we'll call that good. Number 2, logarithmic differentiation. Remember it? Logarithmic differentiation. Remember, that's one we used. There's different places you can use it, but number 2 is a good example of where we would use it because we've got x in the base, x in the power. Do you use power rule? Do you use something else? Well, logarithmic differentiation will take care of it. Remember what we do? ln both sides. Why do we do that? Well, in an ln, you can bring down the power, can't you? So it'd be ln of y equals x plus 2 times the ln of x plus 2. Now if we do the derivative of both sides, the derivative of ln of y, well, it's a little implicit. Would be 1 over y times the derivative of whatever y is. Now, side number 2 here, right side, that'd be product rule, first, times the derivative of the second, which again, the ln of x plus 2, the derivative is 1 over x plus 2. And then the second times the derivative of the first, which the derivative of the first is just 1. And so that leaves me, remember what we do after that then? We're just trying to solve for the derivative, so multiply both sides by y. Oh, and here's a good thing about this one. This one does cancel, doesn't it? The x plus 2's there do cancel, so that's just 1. And plus ln of x plus 2. And to get the right-hand side in terms of x exclusively, what does y equal? Well, that's what we started with. X plus 2 to the x plus 2. So that'd be our final answer. Remember that? All right. We'll do some limits here in just a second, but main thing of our first part of our course was integrals, doing different integrals. So that's what I've got on number 3, and some to follow. A couple of them I didn't mention on this. We have integration by parts. What was the other one? Oh, partial fraction decomposition. I think we've done those multiple times. So I'm not going to review those here on this part, but you might want to before the final. But no, on 3A there, do you see what we might want to do on that? Because that's kind of part of the process, is figuring out what I need to do there. Well, the bottom being a 1 plus something squared, does that remind you of anything? Tangent inverse, yeah. We know that the derivative of the tangent inverse is 1 over x squared. So the antiderivative of 1 over x squared would be tangent inverse. What? Oh, lagoon. That's what I was saying. All right. Stay up there, please. Okay. What I was saying was, side note here, the integral of 1 over 1 plus x squared, if I see that, that's tangent inverse. Well, don't I have something similar here? I've got not 1 over, but I've got 9 over. It's just a number times 1 over something squared. So if I do a little u substitution there, what do I want to sub for u here? 3x? If I sub for 3x, here's why that's going to help me. Of course, du is 3 dx. D over 3 is dx. If I do that, here's what I get. Don't I get something that vaguely resembles tangent inverse? Yeah. So I can get to tangent inverse here that way. So yeah, I have 1 plus u squared du. Well, that's just a multiple of the tangent inverse, isn't it? 3 tangent inverse. Isn't this 3 tan inverse of u plus c? Which u is 3x, so it's 3 tan inverse of 3x plus c. All right, so yeah, if I just have a number over 1 plus something squared, or there's variations of that too, but yeah, that usually comes out to be a an inverse trig. The other ones, I guess of note, if I have, what other ones turn into a good inverse trig? 1 over the square root of 1, just to review that. Yeah, if I have 1 over the square root of 1 minus x squared or something vaguely familiar to that, that's sine inverse. Those are probably the two big ones there. So that's one possibility of integrals. Now, b is not an inverse trig function. Why not? B is not one of those because I've got the x squared on top, right? Got x squared on top. And so what I want to do with this one is another one we have talked about, a really fun one. Trig substitution. Let's try trig substitution on this one. What do you remember about trig substitution? Sort of remember the name? Okay. Well, remember on the trig substitution, depending upon what we have on the bottom, which in this case is under a square root, it's 9 minus x squared. And that kind of ties into what we were just talking about there, but what do I want to substitute here? Well, what I'm going to substitute is for x. It's kind of a different way. This is not u substitution. I'm going to substitute for x something in terms of a theta, either sine theta, tangent theta. And again, it's kind of based on whether you have something minus x squared or x squared minus something. If it was x squared minus something on the bottom, that would be secant. If it is x squared plus something, that's tangent. This is 9 minus something squared, so that's sine. So I'm going to let x be sine theta, 3 sine theta. Why 3? Because I've got 9 there, so I'm going to square it, so it's going to be 9 there. Okay. Now, the other thing, of course, is dx. What's dx? Well, dx would be 3 cosine theta d theta. So let's make that substitution right there. X is 3 sine theta, so the top would be 9 sine squared theta. Then the bottom would be 9 square root 9 minus 9 sine squared theta. And then d theta is 3 cosine theta d theta. With me so far? Reason I do that is because notice here what happens if I factor a 9 out of the bottom. Terms there. Don't I get 9 times 1 minus sine squared? What is 1 minus sine squared? Cosine squared. Let's come over here. All right, so I've got the integral 9 sine squared theta, and that'll be square root of 9 cosine squared theta. Hey, that's going to work out nicely, isn't it? That's just 9 sine squared over 3 cosine theta, and that's going to work out really nicely. Because what happens? 3 cosine theta cancels. Won't always be quite that nice, but you usually get some nice things happening when you do this. So I end up with just the integral of 9 sine squared theta d theta. Which brings up the next review point here. How do I do the integral of 9 sine squared d theta? Well, to do a sine squared, remember that was an even powered trig function. I used the triple angle, double angle, okay. The double angle trig identity, which is, what is a double angle for sine squared? It's on the sheet here. 1/2 minus 1/2 cosine 2 theta. So it's going to be 9 times 1/2 minus 1/2 cosine 2 theta. Or 9/2 minus 9/2 cosine 2 theta. All right, so that's not too bad of derivatives. I guess we could just leave that 9 factored out there. But anyway, this one, the integral antiderivative of 9/2 is just 9/2 theta. What about the 9/2 cosine 2 theta? That's just a little trig substitution. I'm not trig, U substitution. U equals 2 theta. Du would be 2 theta. Or 2 d theta, so du over 2. So won't that be, I don't know how much I need to write there, won't that be 9/2? Then I'll have a 1/2 cosine of u, which is sine of u, which is sine of 2 theta, plus c. Which is a pretty good answer, but it's not the final answer. Final answer, what are we going to need to do there? Well, I was doing the integral with respect to x. I need to go back to x's. All right. How do I get back to x's from the theta? Well, I got to go back to this one, don't I? Forgot about that. Yeah, don't forget about that. All right. Question.
Is it still negative?
Yeah, the antiderivative of cosine is sine, positive sine. Yeah, we're doing antiderivative. Okay. Now, the really useful form of x equals 3 sine theta would be x over 3 equals sine of theta, because if x over 3 equals sine of theta, what does theta equal? Wouldn't theta equal the inverse sine of x over 3? With me there? So that's what's going to go in for theta there. I don't know why I put that. Forget that. C's there. Okay. All right. Now the other thing is, this one is, let's talk about this one, 9/4. What are we going to do about sine of 2 theta? Well, sine of 2 theta, remember we can write the double angle of it as 2 sine of theta cosine theta. Because can I get sine of theta and cosine of theta from the little triangle here? Wouldn't this be, this would also give me the triangle what? If this is theta, wouldn't this be x and that be 3? Well, sine of theta is just x over 3. I've got that. But cosine of theta, adjacent over hypotenuse. What's my adjacent here? A little Pythagorean theorem. Wouldn't it be 9 minus x squared? Would be the adjacent. So it's going to be 9/2 sine inverse x over 3 minus that cancels there, so that would be 9/2. And then sine of theta is x over 3. And cosine of theta is square root of 9 minus x squared over 3. It's all coming back to you, right? And then the nice thing about it, the 9 cancels with the 3's too. So it's just 1/2. I don't have room, but it would be 1/2, or x over 2, 9 square root of 9 minus x squared there. But anyway. Nothing to it, right? Probably have one of those trig substitution problems on the final. All right. So good? Okay. All right, well, we talked about when we had even sines, cosine powers, Now, on number 4, we have an even power and an odd power. We have an even power of sine and an odd power of cosine. Having that odd power is nice because you don't have to use the double angle here. Remember how we do if we have an odd powered sine or cosine, remember what we do? Keep a cosine out. So I'm going to rewrite this as sine. Leave it sine to the 8th x. But then I'm going to break cosine up into cosine squared and cosine x dx. And then change over the cosine squared to sine squared, or sine, which cosine squared is 1 minus sine squared. Because here's what happens. Distribute the sine to the 8th, so it would be the integral of sine to the 8th x minus sine to the 10th x times cosine x dx. And what is now our next u substitution, right? Now we say u is the sine of x. So du would be cosine dx. So du over cosine, so we'll have the integral of u to the 8th minus u to the 10th, because u is sine. And then the cosine of x dx becomes cosine of x times du over cosine of x. Yeah, that's going to take care of that cosine of x. So it's just integral of u to the 8th minus u to the 10th. That's just nice little power rule, isn't it? 1/9 u to the 9th minus 1/11 u to the 11th plus c, but u is the sine. So it's 1/9 sine 9th to the x minus 1/11 sine to the 11th x plus c. Don't forget plus c, right? Okay? All right. Is that all right? So yeah, if you have an odd power of cosine or sine, that's, I mean, if they're both odd, you can take your pick. But definitely if you have an odd power, you want to. Just one other highlight there. What if it had come out to be, if I took the cosine out, and it was cosine to the 4th x? Well, cosine to the 4th is cosine squared squared. So it would be 1 minus sine squared squared. So anyway, just in case that happened. I don't know if it'll happen on this test, but it might. We did. Yeah, you could see, tangent and secant. Those kind of have to, you have to have certain parameters for. It's not as cut and dried as cosines and sines, but yeah, there are. Yeah, for tangent, if you can do secant tangent, hold out a secant tangent or a secant squared, and so. On this one, if they're both odd, take your pick. I would probably pick the smaller one to do the break it off because that'll make it less work. If they're both odd, but yeah. Okay. Number 5, improper integrals. A lot of the improper integrals we did was because one of the limits was infinity, and that was one type of improper integral. And remember, on improper integrals, we're going to use the t-limit stuff. This, however, is, I don't know if you'd call it one of the more complicated ones. I guess I would. Improper integral, because for one thing, what is improper about this? Because I don't go to infinity or negative infinity. It doesn't work for 0. Yeah, I've got a discontinuity in the middle of this thing. So I'm going to have to break it up into those two things, aren't I? So I'm going to have to break it up. It's at 0. So negative 8 to 0. 1 over. I probably should write that as x to the negative 1/3, but I'll do that here in a second. And then 0 to 1. So yeah, break it up at the discontinuity there. Because that's what makes this one improper. I can't go -8 to 1 straight shot, so I have to break it up at the discontinuity because that's why it's improper. All right? Now remember what I do is since I can't evaluate this at 0, I do a limit thing, don't I? A t-limit. So we introduce limits here. I'm going to do what? The limit as t goes to what? 0? If it was infinity, I'd go t to infinity. For the first one, so I'd be -8 to t, x to the -1/3 dx. Let's write it that way. And then the same thing here. And then the good news is that's a pretty easy little antiderivative, right? So I'm going to have the limits. T goes to 0. X to the 1/3, so antiderivative would be x to the 2/3. So it'll be 3/2 times x to the 2/3, right? So -8 to t. Same thing over here. Limit t goes to 0. Of 3/2 x to the 2/3 t to 1. Plug those in. I'll have the limit as t goes to 0 of 3/2 t to the 2/3 minus 3/2 -8 to the 2/3. And then over here I'll have the limit as t goes to 0 of 3/2 1 to the 2/3, which is 1, so it's just 3/2, minus 3/2 t to the 2/3. So what have I got there? As t goes to 0, nicely, what does this go to? T's going to 0, so this goes to 0, doesn't it? That's going to be whatever that is. -8 to the 2/3 is +4, right? It's the cube root of 8 squared. About the same thing happens over here. This goes to 3/2. This goes to 0, doesn't it? As t goes to 0. So it's just -3/2 times 4, which is -6, plus 3/2. Is that negative 9/2?